For this example, I'd like to talk to you a little bit about derivatives, slopes of functions. I get this question a lot from my students. What are derivatives really good for? Why is it that we have to learn about these? Somehow the connection doesn't always get made, and so I want to try to help you with that now. There are lots and lots of good physical reasons why we'd want to know the slopes of functions. Let's say that I'm measuring position of a car as it goes down a racetrack, and I know position versus time. Well, the slope of that position versus time curve is the velocity versus time. And if it's like most racetracks, the velocity isn't constant. So the position versus time isn't going to be a straight line. The reason we need derivatives is to find slopes of functions that aren't straight lines. Slope of a line is just rise over run. I learned that in, junior high school. I suppose you guys probably did too. So let me give you an example here. Here's a function. Now this is just a parabola. I don't know what the physical meaning of this. Maybe this is a function or describes position versus time of some object, maybe a machine part or something. And I want to know the velocity versus time at some point, or velocity of some point. So I want to know the slope of this function. Okay? Well, slope, they always told us it was called rise over run. Rise is the change in along the vertical axis, and run is the change along the horizontal axis, or maybe dy over dx. Okay? If you prefer, we can call this y of x, but it's just a function of x. Okay? So let's pick a point here. That's x, right? For some physical reason, let's say I want to know the slope there. If this is position versus time, maybe I want to know the velocity at that point. Well, slope is rise over run. It's change in this direction versus divided by change in that direction. So let me just put another point here. I'll call it x plus delta x, okay? Where this distance in here is delta x. All right, so far so good. That's that part. Next thing I know is I want to know where these two vertical lines cross my curve. So right now I've got f of x plus, let's try this here. There's f of x, that's that point right there. And this is f of x plus delta x, that's that point right there. So now I know that's the rise and that's the run. That's delta y and that's delta x. Okay? So let's take this one step further. Let's just trust the math and do what the math says we should do. So what I'm going to do here is I'm going to say that my slope equals f of x plus delta x, and I'll get out of your way here in a second. F of x plus delta x minus f of x. So that's this point, this altitude minus this altitude, divided by change in the horizontal direction. So that's delta y divided by delta x. That's a slope. This and this and this are all the same thing. Okay? Well, we actually know what this is. What's this function right here? So I guess I can probably plug that in, right? Let's try that. Actually, let me do it this way. If we're happy with this, I'm going to erase this so I've got some room, and I'm going to start over here again. Okay. F of x plus delta x means I'm going to put an x plus delta x everywhere I see that. So f of x plus delta x. Yeah, let me try that again here. Okay, x plus delta x squared. Okay, everywhere I see x, I'm putting in x plus delta x. I'm just doing what the math tells me to do. Minus 10 x plus delta x plus 2. So there we go. That's what x plus delta x means. Now, what I needed to do was subtract f of x from that. So let's change this a little bit. Well, there's f plus delta of x plus delta x, and I'm going to subtract that function. Okay, so far so good. Again, I'm just doing what the math tells me to do. Last thing I got to do is divide by delta x. So let's just do that. All right, well, looks to me like I could probably simplify that quite a lot. Now, it's going to take a little bit of algebra, but it's worth doing. So let's do that. All right, so here we go. 3, now that's going to be x squared plus 2x delta x plus delta x squared. Now get out of your way. Minus 10x minus 10 delta x plus 2. There's my first term. Minus 3x squared minus 10x plus 2. Okay, oops. Okay, so there's my next try at this. I'm going to go through one more step to simplify this. Okay, 3x squared plus 6. Oops. And again, I'm in your way here. 6x delta x, so 3 times 2, plus 6 delta x squared. I'm running out of room. Let's try this again. 3x squared plus 6x delta x plus 6x squared minus 10x minus 10 delta x plus 2. Okay, now I'm going to subtract all this stuff out. 3x squared plus minus, a minus equals a plus, x minus 2. Whoa, what a mess this is, huh? That's crazy. Well, maybe not. That and that are going to cancel out. That and that are going to cancel out. That and that are going to cancel out. Well, this is looking a whole lot more reasonable here. So let's try this again. 6x delta x plus 6 delta x squared. So I got that term and that term, minus 10 delta x. Okay, well that's looking a whole lot better, isn't it? And I can also divide through by delta x. Remember, delta x is just a number. I don't know what it is yet, but it's just a number. So I can divide through by that if I like. And I got 6x plus 6 delta x minus 10. And I think you can probably see where I'm headed with this. So the last step is the important one. Up till now, all I've been doing is algebra. There's one step to turn it into calculus. And that one step is, what if this delta x is really, really small? And I mean really small. It's as small as I want it to be, but it's never 0. That's a limit. Okay? And this is so small I don't care anymore, but not 0. So maybe it's 10 to the minus 20. That's not small enough. How about 10 to the minus 30 or 10 to the minus 40? Whatever it is, it's as small as it needs to be. If it's that small, I don't care anymore. I'll pretend it's 0. It's close enough to 0 that I don't care anymore. And so what I get is that. That's the slope of that. Now, the interesting part, we didn't decide up front what delta x was, and we didn't decide up front where x was. This is the slope of that curve everywhere. So now we know. Now, since I have the slope everywhere, as the slope is a function of x, I can plot that anywhere. And that's what makes it useful. Now, if you learn the rules for derivatives, remember that you can take a look at this and say 3x squared. Well, the derivative is 2 times 3 times x to the 2 minus 1. So it'll be 6x, and then the derivative of that is going to be minus 10. Well, that's exactly what this is. This and this are related. This is the slope of this. That means this is the derivative of this. You know, mathematicians like to write things in very compact form, so they write it a little differently. But that's the derivative of that.